Okay, so with this we have finished all the introduction from how to go from abelian varieties over the complex numbers to these complex torus and how all the objects that we have in one side translate to the other. What we want to do now is a bit what we did already in the elliptic case, which is to see when we can go from the complex torus side to the abelian variety side. And for that we need to introduce a new object. This is section 3, I think. Okay, so we will introduce the object of Riemann functions. So again, let x, which is v to lambda, be a complex torus we define a Riemann form on X as an antisymmetric form E that goes from V times V to the real numbers, such that, and let's see if I can get all the conditions in one board. It is R linear, satisfies that when we evaluate it on the lattice, then the results that we obtain are integers, so it's integer value over the lattice. For every u and v in the vector space E of I u v, it's the same as E of I v u. And I have to go to the other side for the other part. And the associated Hermitian form H of u v, it's equal to E of I times u v plus I E of u v is positive definite. Okay, so we have this object, and we say that a complex torus is polarizable if one can associate a Riemann form to it. And the result that we are looking for, theorem, a complex torus X is polarizable sorry, wrong phrasing. Complex torus X is an abelian variety if and only if it is polarizable. Okay, so once again, one may ask, okay, but how do I figure out if that's true, right? Do I have to try every possible Riemann form? What happens? So this in practice translates to very easy conditions, again in terms of matrices. But first, because we have seen already everything in elliptic curves, let me give the example of elliptic curves once more. So example, let us consider the dimension 1 case. Take X as the complex torus C modulo lambda, with lambda as we used to take it. So that is generated by 1 tau, with tau having positive image, positive imaginary part. Then we can define H of u v equal to u times the complex conjugate of v divided by the imaginary part of tau. I won't give the details, but you can do it as an exercise. One can check that this Hermitian form, here we are defining H instead of E, but one can translate the, like, from this you can compute what E is and then check the relations. It's easy to check. That H and E and E here is nothing else than the imaginary part of H. Here we had defined it the other way. From E we had gotten H. This is how you get E from H. Satisfy the conditions to be a Riemann form, hence X is an abelian variety. So basically we have what we already knew, which is that every elliptic curve is an abelian variety. Why? Because we have taken them as a complex torus, and we have seen that for any lattice we can define a Riemann form associated to it, hence it's a polarizable complex torus, so it is an abelian variety. So this is not what happens in general dimension, so we have to give the conditions that have to be satisfied so that it is possible. So let me write that. So now we will give necessary and sufficient conditions for that to happen. So we will write it as a theorem. These conditions are called the Riemann relations. And they are as follows. So let X be a complex torus, but we take it already with the period matrix pi. Here, so now X is an Abelian variety if and only if there exists A, which is a 2G by 2G integer matrix, such that, and let me go to this other side, first condition, pi I inverse pi is equal to 0, and second condition, I pi I inverse pi bar is positive definite. So here with the t as an exponent, I mean the transpose. I will write it on the left so that I can do transpose and inverses at the same time. And what one has, well, this is the statement, and here A is the matrix representation of E with respect to the chosen basis for the period matrix pi. And the first condition corresponds to what we had said before, that H had to be Hermitian. The second condition from the condition that H has to be positive definite. And the other conditions, that E has to be integer valued in the lattice and that it's our lineal, just comes from the way we have chosen A, which is just an integer matrix. So it satisfies the linearity, of course, and it's integer valued because on the points of the lattice, the coefficients of the elements we are using will be integers, and so the multiplication in the end will also be integer. And so that we can manipulate a bit these objects that I'm saying all the time that are so friendly and so nice, we are going to prove actually one of the Riemann relations. So let me write it as a lemma, and then I'll go to the other board to write the proof. So with the notation above, just for the sake of being a bit more fast, H is Hermitian if and only if pi I inverse transposed of pi is equal to 0. Okay, let's go to the other side for the proof. Brace yourselves for some matrix manipulation. And I invite you to try to prove the other statement of the Riemann relations, which is that if the matrix on the point 2 is positive definite, then the Hermitian form is positive definite. But for now, we will focus on the first one. First, we need to see how the being Hermitian or not of H translates in terms of E. And that is because we have this matrix A, which we have said is the matrix representation of E. So it's important that we do this first translation. So what does H being Hermitian mean for E? Okay, so let us start by writing what does H being Hermitian mean. So we take H, we take two elements of the vector space, U and V. We can take C to the G if you want. Yeah, this works. Then H of U, V. Let me take W so that they are definitely very different, so it's clearer for you to read. I hope I don't mix them up now as I write. So we have that it is a Hermitian if swapping the two variables is twisted by complex conjugation. So by that I mean that H of W, U is conjugate is equal to H of U, W. Now, if you remember the definition of Riemann form, we can write this in terms of E. And what we have is that E of I, U, W plus I, E of U, W, it's equal to E of I, W, U minus I of E, W, U. Remember that E goes from V times V to the real numbers. So when we write it like this is really real, this is really real. So this equality is an equality of complex numbers. So we have real part equals real part, imaginary part equals imaginary part. So we have E of I, U, W equal E of I, W, U. And E of U, W equal minus E of W, U. This is exactly what it means that E is antisymmetric. And this side here is the other condition we had on E. And now, if we put them all together, we can say that this is the same as writing E of IU, IW is equal. Now I use the first relation, so it tells me that if I have an I multiplying the first vector, it's the same as moving the I to the second vector and swapping places. So if we do this here with two I's, we get that this is equal to minus W, U. Yes, because so we have taken this I and left it here. So here we have I squared, which is a minus, and the I that we had in the first vector disappears. So we have this other expression. And now we just used the fact that it's linearly with respect to the real number, so the minus sign can go out, and the fact that it's antisymmetric, so swapping adds a sign, and we just get that this is equal to E of U, W. So now, what we have proven up to this point is that H is Hermitian even only if E of IU, IW is equal to E of UW. So we can just take out the I's. And the nice thing now is that because we have all this matrix representation, this becomes an equation, a linear algebra problem, basically. So for that, because the formulas are about to get big, I need one more board. This is a very nice proof because it puts together all the techniques and the things that we have introduced so far. And doing all this manipulation really makes us understand and get in touch with what the complex torus's are all about. So, in terms of matrices, we can write, let me do a line here so that I'll have space. U equal pi of x, v equal pi y, where x, y are vectors with real entries of length 2g. And then E of u v is equal to E pi x pi y. And this is what I meant by saying that A is the matrix representation of the map of the Riemann form, is that this is just the transpose of x times the matrix A times y. This is the choice that we are taking for E. And so now we want to see exactly that for this choice of E, we have the condition that we saw before. So E of I, U, I, V, sorry, W, so that we can keep it clean. So this is W, W, and it works. U, W, it's equal to E of U, W. The one thing that we are missing in matrix form is this multiplying by I. But for this, we go back to the definition of the homomorphisms. So we write the homomorphism I'm going to write it with the brackets as we said with the multiplication by m, although it's not an integer now, but so that we are clear, this is a homomorphism from the vector space to the vector space in matrix form. And actually the vector space, it's just C to the G, the way we defined it before. So when you say multiplying by I, it's just the identity multiplied by I. And we have that I times pi is equal to pi times a matrix I, which has entries 2g times 2g into integers. Here we don't mind where the prime is because it's just an endomorphism. We go from one towards to itself. And this allows us to write I as a we can exactly write this matrix. So we obtain, and how we do this? Well, the trick here is that these matrices are G by 2G, but if we think of the condition that pi has to satisfy for it to define a complex torus, is that the matrix where we take pi and pi conjugate, it's a non-degenerate matrix. So if we take both this condition and the condition written with the complex conjugation, the I on the right, it's the same because it has entries on the integers, right? So this is real. This doesn't change by complex multiplication, conjugation, sorry. And everything else does. So we can write that Ig, the complex conjugate of Iig is minus I by the identity. Here we have pi conjugate is equal to pi conjugate times this matrix I, that again doesn't change because its integer, its entries are integers, so complex conjugation doesn't change them. Hence, now we know that this is not degenerate, so we can invert it, and we get exactly what I is. I is equal to pi bar inverse I identity minus I identity. Here I'm writing these matrices as block matrices. In these two blocks we just have zeros. I don't write them to just save some chalk and some time and some energy. And now we have what capital I means, is. So if we look at this equation that we had matrix-wise now, the equation, I think I already used the star, so I'm going to call it 2 stars. Is written as, and what do we mean? Well, having I times U matrix-wise is having I, so the rational representation of I multiplied by the 2G representation of the point. So basically we get I transposed times A times I, it's equal to A. And now we just have to replace this by the very long expression of I, and we do some matrix manipulation and we end up obtaining the condition that we had in the statement. Let me write it. Bear with me, it's going to be long. But I think it's very interesting to see this manipulation. Again, working over the complex numbers allows us to really understand the things that we are working with, so when later you work over a general number field, you have a more clear idea of what you're doing. So, okay, this is pi bar, I 1g minus I 1g transposed pi bar inverse A, and start again, pi bar inverse I n. Here I also should have the transpose, but it's diagonal, so it's just itself, minus I 1 n's or g's, if I miss some, pi bar here remember that if we take the transpose of this matrix in this side in a product, it just switches the order of the matrices. So that's how we obtain the expression there. So it's exactly what we have here, the swapping of the order. So now here we have the inverse, I pi, this is equal to A. And now, well, again, this is non-degenerate, this is non-degenerate, so we can pass them to the other side. Let me write it once more. We have I 1g minus I 1g. I write it so that you don't have to. You can follow with what I'm writing. Pi bar inverse I1g minus I1g equal T pi bar inverse A pi bar inverse. So now I will call this, so this here we will define it as V inverse. I just write the inverse because we have two inverses, so maybe it's better to just take the inverse of everything and just having the inverse on A. And then this is exactly the same, so V inverse. So what I will do next is to take the inverse of the whole equation and write it blockwise. So develop these products so that we have a by blocks G by G blocks matrix where we can actually take the equality and see what it means for like the smaller pieces that we have in this. But first let me write what B is block by block. So B is equal to pi bar. So now we take the inverse of this, so the translate as when we took the translate, it switches the order of the matrices. So we have pi conjugate, A inverse, and the transpose of pi conjugate, which is just the transpose of the blocks in a row now. So we have transpose of pi, transpose of pi bar. And now we just take the product. First look at the first piece. And we have pi I inverse, pi bar I inverse times transpose pi bar. And now it's just this, as always, right, row per column. So we get 4 blocks that are exactly pi I inverse, the transpose of pi A inverse, the transpose of. Now we have the conjugate, so the first column, second row, it's the second row of the first column of the second. We continue. So we now get pi A inverse, the transpose of P conjugate A inverse, transpose. So you can see it's tricky. You have to tinker with all the matrices. But now we have what B is blockwise. So it's easier to do this product because this is always blockwise on blocks G by G. And so we write it once more. I will write now the left. So we have that minus I 1G I 1G times V. I take the inverse of the left side now. So the inverse of this matrix just moves the sign to the top. So we have minus I, the identity of dimension G, I, the identity of dimension G, times V, times the same thing again. And now we take V as the blocks that we had here. So having this minus I means that this top corner will be multiplied by minus I squared. This and this will be I times minus I, so that's 1. And this will be 1 squared. So what we get exactly is minus I times minus I is minus 1. So minus pi I inverse pi transpose, pi conjugate A inverse T pi conjugate, pi, not here, here A inverse, and minus pi bar A inverse the transpose of pi bar. Okay, so with this we have written blockwise the left side and the right side. Let me name them so that it's easier. Right hand side, left hand side. Remember that we have taken the inverse of the equation, but in any case what we have now is that this matrix by blocks here is equal to the matrix by blocks here. We don't really care about the top right and bottom left corners because they are exactly the same, but when we do this equals to this blockwise, we get that something is equal to the same thing in negative, so that just means that it is 0. And with this we have seen how we can see that a complex torus is an Abelian variety in a very explicit way with the matrices. So this is the first Riemann relation. It's the condition that has to be satisfied by the period matrix and the Riemann form that we have chosen. And there's still the second condition that I invite you to play a bit with and see that if you can manage to get it. But this is exactly the condition in the statement, so this completes the proof. Okay, so we have finished introducing all the objects that we wanted, but remember that yesterday when we were talking about elliptic curves, we chose this way of taking a basis for the lattice that was nicer and that allowed us to define theta functions after, which is something that we also want to generalize for complex tori and Abelian varieties. So let me do that for this case. So this will be related to the Riemann form, and basically because that's the condition that we want that we have for a complex torus to be an abelian variety, right? So yes, we say that a basis of lambda is symplectic, only one m, I think. If the matrix associated to the Riemann form E with respect to that basis is 0 d minus d 0, where d is diagonal with entries d1 dividing d2 until the end. Okay, so this is the diagonal matrix, the same on the top and the bottom, and the entries divide each other progressively like this. And yeah, this only depends, note that this only depends on the basis of the lattice, not on the one that we choose for the complex vector space. In fact, if you look at the condition that we had for a complex torus to be an abelian variety, we could actually multiply by a matrix in front and behind, which would be the equivalent of changing the basis of the complex vector space, and we would still have that this is 0, because, I mean, it's the 0 matrix. Whatever you multiply it with, it stays 0. So yeah, that's the idea. And for what we will be doing later, we will mainly, at least for my part, I think that with Stefano maybe you will look at some cases where this is not the identity. But in my case, in my course, we will mainly focus on complex story with Riemann's form of type D. So basically, for any complex torus, it's possible to take a symplectic basis of the lattice, and then we always obtain a matrix of this shape, and this shape is what determines what we call the type of the Riemann form, and we will later relate this with isogenies and the degree of an isogeny, etc. But for now, let's keep it at that. And in that case, then we can do something similar to what we did the previous day. I will focus on the case, sorry, I didn't finish the sentence. We will mainly focus on the complex story with Riemann forms of type D equal the identity. Yes, okay. So in this case, but we can also do it in the general case, we will see that the vectors lambda g plus 1 up to lambda to g, so the second half of the basis of the lattice, which is the one that has this D block, that in our case is the identity, form a basis of the complex vector space of the torus, and if we choose them as such, then the big period matrix is of the form omega identity, because remember that the big period matrix, we obtained it by writing the basis of the lattice in terms of the basis of the complex vector space. And of course, if we take the basis of the complex vector space to be the second half of the basis of the lattice, the latter is just the identity matrix of dimension G. And this is a matrix omega that is G by G with complex entries, and we have that omega is symmetric and with positive definite imaginary part. These two conditions on omega actually come from the Riemann relations. I invite you to take them and see what happens in the case where the period matrix is of this shape and the Riemann form is given by this matrix with D equal to the identity. And you will see that exactly what it gives you is that this matrix omega has to be symmetric and with positive definite imaginary part. And so let's give a name to this period matrix. So we call omega a period matrix of complex vector. See that now I've removed the big part of the name, and we define the Siegel upper half space AG as follows. So we have HG equal the matrices G times G with complex entries such that omega is symmetric, so the transpose is equal to the function itself as to the matrix itself, and the imaginary part of the matrix is positive definite. I ate half the board again. And what we also have, one can write, is that then I won't write the details right now, but one can take then the definition that we took for homomorphisms and their matrix representations and see how homomorphism of complex torus that are represented by a small period matrix affect the period matrices. So one can write the relation between the period matrices in both sides in terms of the rational representation of the matrix. Again, this is matrix manipulation of block matrices. So I invite you to look into it and try to write it down. We can always comment on it and discuss it over the platform of the course. But now I want to introduce one last object on the Abelian variety side of things, because we have actually been talking about this object on the complex torus for a while now. So for now, we have always introduced a concept on the Abelian variety side of things and translated it into the complex tori. And now we have actually done the opposite. we have been talking about this Riemann form, and we talked about the complex torus being polarizable, and we are now going to see what the polarization is, and that basically motivates the name that we have seen. So let me go to this side. I think that I'm at the fourth, otherwise just okay. We go now into one of the maybe a bit more tricky concepts, because until now everything was kind of plain and basic, very easy to see in the elliptic curve side of things. With the matrices it was nice. Now I'm gonna use some bigger words. But just keep in mind that I'm in the complex side of things. Everything that I'm defining, it's what we have seen in Riemann forms. And in the end we will go back to the complex side and see a bit more. Just bear with me. So we go back to the Abelian variety. Okay, so now we define some concepts, some more objects related to the Abelian variety. Given an Abelian variety A defined over K, we define the Picard group of X as the group pick of. Sorry, I'm gonna be switching X and A's all the time. I'm trying to keep X, Y for complex tori, A, B's for Abelian varieties, so that we are clear on the side. So the group pick of A of isomorphic classes of line bundles on A, but defined over the algebraic closure of K, given a line bundle L on A over the algebraic closure, we define the homomorphism and here I'm kind of already hitting a proposition, because one should actually prove that this is a homomorphism. But let me write it here. Phi of L that goes from the set of points of A over the algebraic closure of K to this group that we've defined, pick of A, such that for every point X, we send it to XL tensor L inverse, where Tx stands for the translation by X on a k bar, and the L with the bracket, so the class of a line bundle, it's exactly that, right? So it stands for the isomorphism class of L in the Picard group. Okay, it's a bit, but we power on. Okay, so we have defined this group, the Picard group of A, this homomorphism. We define one more thing. So we also define the pick 0 of A as the subgroup of pick of A consisting of classes of line bundles L such that this homomorphism that we have defined is 0. And why do we do that? Well, this new object it is the group of k bar points of an Abelian variety over k, and we call it, so we call this variety for which we have found the k-bar points, the dual variety of A, and denote it A with a hat. And with this setting, well, as always, now we introduce homomorphisms and how they translate. So a homomorphism of Abelian varieties F from A to B induces a map on the respective Picard groups that we will denote F upper star, and it goes from the Picard group of V to the Picard group of A, and it maps the pick 0 of B to the pick 0 of A, so actually we can take the restriction and this will give us what we call the dual homomorphism of F So now with all this notation in mind, we define a polarization on A is an isogeny lambda, which is actually given as the homomorphism associated to a certain lattice, line bundle, where the line bundle, let me make the chalk stop talking. Where the line bundle is ample, on the Abelian variety over L, which is a finite separate extension of K. We say that the polarization is principal. Well, I mean, because it is an isogeny, to it we can associate a degree, and we say it's principal if it's of degree 1, which means in practice that the polarization is an isogeny. And once that we have defined polarization, we can say what is a polarized Abelian variety. And keep in mind that these are two different objects that have two different arrows or morphisms associated to them. So we can look at Abelian varieties by themselves, and that gives us some results. Or we can look at Abelian varieties as polarized Abelian varieties, so a pair Abelian variety polarization, and that has some other results. The same way that with complex torus, we can look just at the complex torus, and we can look at the complex torus together with a Riemann form. So a pair x, sorry, did I write any more x's that were a's? No. A lambda is called a polarized Abelian variety, and we have two polarized Abelian varieties, A lambda V mu are isomorphic, and again here I'm talking about isomorphism as polarized Abelian varieties, which is different to isomorphic as Abelian varieties, because here we had the condition that has to be satisfied on the polarizations too. So we say that they are isomorphic if there exists an isomorphism F between A and V, and here I am talking about an isomorphism as an isomorphism of Abelian varieties, and now I add the extra condition for it to be an isomorphism of polarized abelian varieties that is compatible with the polarization that is, and let me draw the following condition as a diagram because I think it's more visual and it will help you, that we have here A and B. Here we have the isomorphism. Now here we have that we go to A hat. Here we go to B hat. And this is the polarization of V. This is the polarization of A. And this is the dual homomorphism. And we want this diagram to commute. So what we mean by this is that lambda is equal to the dual after the polarization on V after the initial isomorphism. Okay, so once more, we go to the case defined over C, and with this we will finish for today. A complex polarized abelian variety is a complex torus together with a Riemann form, as I announced at the beginning. And now, I mean, this is an isogeny of abelian varieties, right, between an abelian variety and its dual. So we again have all the tech that we have seen of going to the shape of a matrix. And the Riemann form is then nothing more than the rational representation of this isogeny that we are defining between the abelian variety and its dual. So that means that the degree is represented by the determinant. And that's the last thing that I want to say, which is that the determinant of the matrix representation of E is the degree of the polarization as we saw at the beginning when we talk about the degree of an isogeny. And so we have that it is principal even only if the determinant is 1. And furthermore, you can think of the shape of the Riemann form when we take a symplectic basis. In the general case, we get this matrix that had entries 0, D, minus D 0, and that gives you an idea of the different possibilities for the degree of polarization. But as I was saying, for the sake of what we will see in the next lecture or the next video, we will be focusing on the principal case. So in that case, we had that D was the identity, and so the determinant that we obtained is 1. And that's it for today.